Differentiability. Remember that a function f is differentiable at a point x equals a if this limit exists. In this video, we're going to look at ways that a function might not be differentiable, and we'll see pictures of each. So let's start with this picture. This is a picture of a function that's not differentiable at x equals a. And why is it not differentiable at x equals a? Well, if we look at x equals a and we think about what this difference quotient is, what's going to happen to that difference quotient? Well, we'll take f of x minus f of a over x minus a and we'll get a slope. But as we let x approaches a, that slope is going to approach a vertical line. In other words, this limit is going to approach infinity. And if that limit approaches infinity, we're going to have a vertical tangent. And whenever we have a vertical tangent, the function's not differentiable. That is, when we say that this limit as x approaches a of f of x minus f of a over x minus a has to exist, we mean it has to come up and be a real number. It has to work out to be ordinary real number. It can't go off to infinity. If it goes off to infinity, this limit is said to not exist. In that case, we'd have a vertical tangent, and we'd say that the function is not differentiable at that point. So that's one way a function could not be differentiable. Here's another, and this is a classic way a function could not be differentiable. This is a function that's not differentiable at x equals a, and the reason is because there's a corner. And so you can see that the slope coming from the left is going to be a slope like this, whereas the slope coming from the right is going to be some slope like this. So the slope from the left is not going to equal to the slope from the right. That's an example of a corner, and it's another example where this limit is not going to exist. The limit won't exist because the limit from the left will not be equal to the limit from the right, and so that means that this limit won't exist, and it's a classic way that a function might not be differentiable. Notice that both of these functions are continuous. So this is a nice continuous function, and this is a nice continuous function. So both of these examples are examples of functions that are continuous at x equals a, but not differentiable at x equals a. So remember we say that if a function is differentiable at x equals a, it has to be continuous. Here's an example that shows that a function can be continuous at x equals a, but not differentiable at x equals a. Same thing here. The function's continuous at x equals a, but not differentiable at x equals a. So let's look at one more example of where a function is not differentiable. This is an example where a function is not differentiable at x equals a. It's not differentiable at x equals a because there's a discontinuity. Whenever there's a discontinuity, the function cannot be differentiable. There's no way. That follows from the fact that if a function is differentiable, then it's continuous. And we get from that fact that if a function is not continuous, then it's not differentiable. It's a logically equivalent fact. And we can figure out why this function is not differentiable. Note that it's not differentiable even though the slope from this side might be the same as the slope from this side, or it might look like the slope coming along here might be the same as the slope coming along here. According to this definition, it's not differentiable. And the reason is because we don't get to choose two different values for f of a. In other words, if f of a was up here where the black dot is, that's actually where f of a is, the limit from this side would be fine. It might be 0. But if we choose that for f of a, we can't decide when we're coming from this side to move f of a down to this open circle. F of a has to stay up there. And if f of a stays up there, if we think of the difference quotient coming from this side, we're going to take f of x minus f of a, which is going to be this huge jump, divided by x minus a. And so as we come from the left, since f of a is way up here and f of x is way down here, this limit will go off to infinity, and the limit won't exist from the left. There's no way to fix it. There's no way we can move f of a to a point that's going to work from both the left and the right because it's discontinuous. So these are three different types of functions that have a point where the function is not differentiable. And so that helps us understand the concept of differentiability by understanding the places that are typical for where a function is not differentiable.